We've talked about charged objects and where charged objects come from, right? Gain of electrons, loss of electrons, how it gets a negative charge or how it gets a positive charge. But we haven't really talked about how that happens. Well, the next few minutes, that's what I want to talk about. There's two main ways of charging objects. They are charging by conduction and charging by induction. Conduction always involves a transfer of charge. You guys remember what a Q means? Charge. So it always involves a transfer of charge. If you walk up to somebody and your sock feet on the carpet and you touch them with your finger and you shock them, there's a transfer of charge taking place there. Electrons transferring from your finger to theirs. That's charging by conduction. It always involves a transfer of charge. Now, conduction usually, although not always, usually involves two objects touching. Once again, when you walk up on the carpet to somebody, rub your feet against the carpet, build up a charge in your body, and touch them to shock them, that's conduction because charge was transferred. You also touched them. You also made contact with their finger. But you guys might know that sometimes you walk up and you're kind of a little bit nervous about touching the finger, so you just kind of do it really, really slowly, and all of a sudden the charge jumps from your finger to theirs before you actually touch. That's still charging by conduction because it was a transfer of charge. It's just that it didn't actually require the touching. Usually conduction involves touching, but sometimes things can be close enough together that it's as if they're touching. That's what happens with lightning. Okay, it's raining outside, and there's a big buildup of charge, a big buildup of electrons on a cloud. And that charge jumps from the cloud to the ground. Well, that's conduction, because it was a charge transfer from the cloud to the ground. The cloud wasn't touching the ground, though, but they were close enough that it was as if the cloud was touching the ground. So it always involves a charge transfer, and it usually, but not always, involves touching two things together. Now, we break conduction down into two subcategories. One's called charging by friction. When we charge by friction, we simply rub two things together. If you take the balloon and rub it against your head, the balloon becomes charged, as does your hair become charged. That's charging by friction. If the balloon and your hair were both neutral to start, and you rub the balloon against your hair and it became -5, then what will your hair become? +5. And if you were asked to explain how you got that, you would say, well, that's the law of conservation of charge, principle number 7, right? It's governed by the law of conservation of charge. The total charge on your hair and the balloon was 0. The total charge on the hair and the balloon has to remain 0. Well, if the balloon becomes -5, then the hair has to become +5 to stay at 0. Now, charging by contact is really what we already did. This is when we touch two things together and they want to balance out. I'll say touch and balance, but I'll put balance in quotation marks because they don't always balance, right? They try to balance, but if you have something that's bigger, then it's not going to perfectly balance, or something that's pointed, it's not going to be perfectly balanced. Charging by contact is often just called charging by conduction. We often don't use its subcategory name to it. We just kind of lump it all together as conduction. So realistically, even though there's a couple of different ways of charging by conduction, if you see the term conduction, charging by conduction on a test, what it probably means is the touch and balance thing. Does that make sense? The problems that we just did, example number 2 and example number 3 a little while ago. Both of these are governed by the law of conservation of charge. If you rub two things that are neutral, one becomes +5, one becomes -5, well, that's dictated or governed by the law of conservation of charge. If you touch two things together, one that's -3 and one that's -5, and they both become -4 and -4, well, then that's governed by the law of conservation of charge as well. Now, the other category of charging objects is by induction. Induction never involves a charge transfer. Now, I'm going to put a little star by that because I have to explain that in a moment, that it never involves a charge transfer. Remember that it never involves a charge transfer, but with a little asterisk that I'll explain in a few moments. It never involves a charge transfer, and it never involves touching. We have two subcategories of charging by induction. One is called the temporary separation of charge, and the other is a permanent charge. I'm going to draw some pictures to explain to you what each of these things means. Let's say we've got a neutral object, a neutral conductor. 3 positives, 3 negatives. It doesn't have to be 3 and 3, right? 1,000 and 1,000, 10,138,000, 10,138,000. As long as it's an equal number of protons and electrons, it's neutral, right? This is neutral. I'm going to bring a positive object nearby. Now, I'm not saying that this is just protons. There's electrons there as well, but there's more protons than electrons, meaning that I have a positively charged object. Now, let's assume that I bring them close by so that they interact with each other, but they're not touching, and they're not close enough for charges to jump. If I bring this too close, what we might find is that electrons jump from this guy to this guy. Well, then that's not induction. That's conduction, right? Even though they're not touching, it's a charge transfer, so that would be conduction. Let's assume that they're far enough, they're close together, they affect each other, but they're far enough apart that electrons don't jump or don't arc from one to the other. Tell me, what's going to happen to the protons in this neutral object when I bring a positive object nearby? They want to get pushed to the left side, right? But they can't be pushed to the left side because they're tightly bound in the nucleus, which means they're going to pretty much stay where they are. So nothing's going to happen to those protons. Although they want to be pushed away, they can't really go anywhere. All right, what's going to happen to the electrons? Yeah, they're going to be pulled over to the right side. And they will be pulled over to the right side because they're not nearly as tightly bound in there. Take a little bit of force, you can pull them away easily. This creates, notice, one side that is predominantly negative and one side that is predominantly positive. That's a separation of charge. Now, I've drawn it in a little bit of an exaggerated way. The reality is the left side will have some negatives still there, and the right side will still have some positives. But you'll have more positive on the left and more negative on the right. That's a separation of charge. The total charge is still neutral, but it's a separation of charge. It's split up. Why do we say it's temporary, though? Any idea why it would be temporary? We didn't call it a separation of charge up there when we listed the types of induction. We said it was a temporary separation of charge. What does that mean? Yeah? When would it return to its original state? Yeah, if I take this away, if I take this positive away, then there's no reason for those electrons to stay sticking to the right-hand side. They're going to go back more or less to the way they were before, right? Scattered randomly throughout this thing. Does that make sense? It's a separation of charge, one side positive, one side negative, but it's only temporary because as soon as I take away the thing that's doing the charging, they go back pretty much to the way they were before. Yep. How do you know what, sir? How do I know induction? Oh, that's a good question. I don't know, actually. You mean like an induction oven or an induction stove? Yeah. Okay, like a stove top? It's a good question. I think that it works based on principles of magnetism as opposed to electricity per se. The electricity would generate a magnetic field, and then I think it's something with that, but I'm not positive how that produces the heat. How it produces the heat in it. Yeah, I'm not sure. It's a good question, though. Yep.
Not how they make magnets, like they get it really hot, do that, and then they let it cool down, so that it sort of like hardens, and then it still stays in that state.
Yeah, not exactly. Not exactly. It would probably be done when it was hot. I'm not even positive about that, but I would imagine that it would be done when it was hot. but it wouldn't be done by just trying to charge it, right? Remember that there's a difference between a positive and negative charge in a north and a south pole. Okay, north and a south pole, they're magnetic. They are electrically based, like they can be produced by electricity, but not just simply by charging something, positive and negative. Okay? All right, let's draw another one here. Let's draw our neutral object again. Same number of positives, same number of negatives. Let's this time, they'll bring a negative object nearby. A negative object nearby. What's going to happen to the protons in this neutral object now? Well, there's a quick one-word answer to this. What's going to happen to the protons? The answer is nothing. They're going to stay where they are. They want to move. They want to be pulled over to the right-hand side, but they can't because they're too tightly bound in the nucleus. But these electrons will do something. What are they going to do? Yeah, they're going to be pushed away to the left. So they're going to go over here. That leaves us with predominantly a negative side on this one, on this side, and predominantly a positive side over here. Once again, a separation of charge that is temporary, because when I take this charging object away, the electrons are going to be randomly distributed again and be even. Now, we told you this yesterday and we reviewed it earlier today. Charged objects attract neutral objects. Why? Now you're going to find out. The side of the charging object, this side of the charging, the charging object closest to this side is oppositely charged. Okay, notice what happens here? Okay, when I bring a positive nearby, the side that's closest becomes negative. If I bring a negative nearby, the side that's closest becomes positive. Why do charged objects attract neutral objects? Well, because when we bring a charged object nearby a neutral object, we induce a temporary separation of charge. And then the side that's closest is opposite. So why do charged objects attract neutral objects? Basically because opposites attract. And the side that's closest with this temporary separation of charge has become opposite. Does that make sense? That's why you can't get a proton attracting a neutron, because you can't get a separation of charge in a neutron. That's it. You can't separate charges in a neutron when there are no charges in a neutron. Okay. How does this become permanent? How do we make this permanent? This is temporary because we take this charging object away here and electrons go back to the way they were before. How do we make it permanent? We attach what we call a ground, or a grounding wire, sometimes we call it, which could be literally a wire that goes into the ground. Your house has a grounding wire. That third prong of your plug-ins is a grounding wire. And it's attached ultimately to this copper wire, this copper cable that's a little bit thinner than the thickness of your pinky finger, that literally goes from your circuit breaker panel into the ground. You may have seen it before. Sometimes it goes on the outside wall of your house, and it's not even covered up sometimes, this ground wire. Usually it's covered up by the tube, okay, by the plastic tube, the PVC pipe that takes the wires to your panel, like your electrical meter, right? But it literally just goes into the ground. If you have a short circuit in your house, then all these excess electrons will go through this ground wire into the ground. And the Earth is huge, so it can handle a few extra electrons. Your house can't. Your house will burn down if there's a few extra or a lot of extra electrons. The ground can handle it. So a grounding wire is literally, or can literally be, a wire or a conductor that goes into the ground. So we attach a ground wire here. What happens in the first diagram? Well, this positive object sucked negatives to the right-hand side. Well, if it's attached to the ground, it's going to suck negatives from the ground up into this as well. Now we've got not only a bunch of negatives on the right-hand side, we've got a whole bunch more negatives that have been sucked up from the ground. What's the charge on this neutral object now? It was neutral, but charges were separated. Now it's negative, right? Now there's more negatives than positives. Still temporary, though. How do we make it permanent? How do we prevent those electrons from going back into the ground? Get rid of the ground wire. Cut the ground wire. Okay, remove that ground wire. Remove the connection to the ground. Remove the ground wire. Remove whatever it is that's connecting it to the ground, right? If I have the static ball like we did yesterday, the Van de Graaff generator, and I put my hand on it, okay, after I turned it off but it was still charged, then I would ground it because I would provide the path for the electrons to flow through into the ground. Okay, if I let go of it, then I would be removing the ground wire. Now there's no way for the electrons to get back into the ground. Now you're left with a permanent negative charge. What about this one? Negatives aren't going to get sucked up from the ground here. Rather, negatives are going to get pushed down. Yeah, pushed down into the ground. Now these guys right here are gone. Now it's positive. If I want to make it permanent, I cut the ground wire. Or remove whatever it is that's connecting the ground to the object. Make sense? In your example problem booklet, you see a picture of an electrostatic precipitator. What this is basically an air filter. You have an air filter in your furnace. Everybody does. It's just a mechanical thing, though. In most cases, it's just a mechanical thing. You have all these fibers that are so close together that as air goes through it, it pulls out dust. But it is limited by the size of the dust because you've got these fibers all mixed together. If the fibers are smaller than the holes, if the dust is smaller than the holes in between the fibers, then the dust is just going to pass through with the air, right? We can use something called an electrostatic precipitator to pull out more pollutants or more dust than you can with a mechanical filter like this. And it might look something like this. Okay, you're pushing air through this thing. Maybe there's a fan over here somewhere, and it pushes air through this device. And this air has pollutants in it. It has dust in it. It has all these different particles in it. These particles are these little green balls and these little blue balls that you see there. These green balls are the neutral dust particles, or the neutral pollutants. These are the pollutants that we want to suck out of the air or take out of the air before we pump the rest of the air through the house. Now, as we pump these through these blue rods here, which are negatively charged, we know those are negatively charged because they're closest to the negative side of the battery. If they're touching the negative side of the battery, then they become negatively charged. This air blows through these rods here, and these dust particles within the air touch these rods. These dust particles become what? They were neutral. They touched negative. When neutral touches negative, the neutral becomes negative. That's called charging by what? Induction or conduction? Conduction. They touched and charged was transferred. Okay, so we charge these dust particles and these pollutants negative by conduction. Now, once they pass by these little blue rods, they're negatively charged, right? So the pollutants are negative. They're still there, but they're negatively charged now. Now, as they pass through these positively charged rods, or these positively charged plates, I should say, and we know these plates are positively charged because they're closest to the positive terminal of the battery. What happens now to these negative pollutants as they go through these plates? Positive attracts negative. So we've got these dust particles that are negative. The positive plates attract these negative dust particles, and then these negative dust particles stick to the plates. What goes out the other side? Air minus the dust particles, right? Okay, minus the dust particles. One more quick little one that explains this. Okay, this is a metal fence, a wrought iron fence around the pool in my backyard after I win the lottery next week. Okay, what's going to be the pool in my backyard when I win the lottery next week? I want to paint my fence. Okay, but I don't want to take a paintbrush and paint my fence because that takes too long. So I want to spray it. But then there's going to be a lot of overspray, and the deck of my pool is going to get all messed up by the black paint, and you're going to get paint in the water, and it's going to be just a big mess. So what I use is electrostatic painter. Instead of just blowing the paint at it, I charge the paint before I blow it at it. In this electrostatic painter, you might have a rod that's charged negative or positive, doesn't really matter. Let's make it negative. as the paint goes by this negative rod, the paint touches the negative rod and charges by conduction, touching, a transfer of charge. The paint particles become negative. Now, as the paint particles are blown towards this fence, what happens? As the negatively charged paint particles are blown towards this metal fence, they become attracted to it, right? They become attracted to it. So not only am I blowing paint towards the fence, I'm blowing paint towards the fence and using the fence to literally attract the paint. Now, this paint is charged, but that's okay because this fence is connected to the ground. So any excess charge will drain into the ground. Now, it doesn't mean that you're not going to get any overspray, but you get a lot less overspray and a lot cleaner job because as you're blowing paint towards it, right, kind of fuses to the object, but as you're blowing paint towards it, it also goes around it. But if this was just a regular paint, a regular air compressor paint gun, then the paint would go off like this and get on the deck of your pool or inside in the water of your pool or whatever. But because this is charged and attracted to the neutral object, a lot of it will actually get pulled back around and paint the back of the object. So you lose a lot less. It ends up being a lot cheaper, but it also ends up being a lot cleaner. They'll do this when they paint cars at a factory. They'll use electrostatic painting. Main reason, not to be cleaner, but the main reason is to be cheaper, right? You waste a lot less paint. There's a nice clean job. It's a lot more even, and it also creates a lot more waste, which is a lot cheaper.